Well, and thank you very much of all of the participants in this colloquium. And first, and many thanks to Natalie for the participation in this colloquium. And it's a pleasure to introduce Natalie Paquette, and is assistant professor of physics at the University of Washington in Seattle. And 20 2017 and before, Natalie earned her PhD in Stanford and in 2017 and before joined University of Washington and held postdoctoral fellowship at the Caltech in the Institute for Advanced Study in Princeton, New Jersey. He brings together deep mathematics and physical insight from the studying phenomena such as moonlight, today's topic, to exploring the role of homological algebra in complex geometry, in holography and scattering amplitudes. Thank you, Natalie. Go ahead.
Okay, thanks so much for the introduction and for the invitation. So I know this is a mathematical audience, so what I'm telling you about today is some work that I did a few years ago, actually through my PhD and early on in my postdoc, but I think it's a really fun story at the interface of mathematics and physics, and I feel like it's a nice way to introduce some physics using a curious mathematical correspondence. So I hope that it's enjoyable for this audience, and please feel free to interrupt and ask questions along the way if you'd like to. So the mathematical subject that I'll tell you about is called moonshine. And if you aren't familiar, of course, you can think of the light of the moon as some mysterious and beautiful thing, but moonshine is also a very alcoholic type of liquor. And people were brewing it sort of illegally during the Prohibition in the United States. So it also has the feeling of something illicit, something that is illegal and shouldn't be happening. And so it involves a mathematical correspondence between two different parts of math. And before people understood it, it felt like something very mysterious and illegal was happening. And that's why it's called moonshine. So let me tell you about how that goes. Okay. So let's first talk not about the specifics of moonshine, but let me just give you a flavor of the sort of subject that it is, and then I'll introduce piece by piece all of the important players in this story. So today is going to be a celebration of sort of weird and rare mathematical structures and how they appear in physics rather surprisingly. So often in mathematics, we have classification problems, and usually there's some nice orderly families in this classification, and often there are some leftover oddballs. And I'll talk about some specific ones today in the context of group theory, but for example, the Platonic solids or exceptional Lie algebras and other objects like that, they're called exceptional in mathematics because they're sort of a finite and special set of outliers. So the sort of structures that seem very weird, not necessarily something that seems to fit in naturally anywhere, they seem like they're leftovers. And so the fact that these things actually appear in physics is maybe a bit surprising. Because normally, when we think about physics, we think of beautiful and uniform structures that sort of appear everywhere and are very generic. You know, we use calculus in physics, we use group theory, differential geometry. I'll talk more about group theory in this talk as well. All of these are very uniform structures, and they describe a very wide range of phenomena. But exceptional structures are, again, these rare and special objects, and I think it's a very fun fact that they do often appear in physics in deep and surprising ways. And so moonshine is about exceptional structures in mathematics. And I'll explain that at least some instances of these moonshine phenomena can be understood and unified using the physics of string theory. So in particular, as I'll explain, moonshine is a correspondence between some objects in group theory, in particular the theory of finite groups, And then nice functions or objects in number theory, analytic number theory, called modular forms. So moonshine is about a mysterious relationship between these two objects from very different parts of mathematics. And there are also more modern examples where algebraic geometry is involved as well, although I won't get into that in this particular talk. But all of these mysterious correspondences and relation between these two very different mathematical objects that seem to have nothing to do with each other can actually be mediated and understood very naturally using some string theoretic constructions. So I want to tell the story of how that works in more detail. So I'm a physicist, so let me also just explain maybe a little bit about why I, as a physicist, might be interested at all in these very surprising mathematical correspondences, and why other physicists like me also find some of these objects very interesting and worth pursuing. So you may have heard or studied or know that, say, Einstein's theory of general relativity, which describes gravitational interactions and the curvature of space-time at long distances, is formulated in the language of Riemannian geometry. That's the basic mathematical structure that allows us to write that theory down and understand it. But we don't know what the corresponding mathematical structure is for string theory. We don't know the analog. Riemannian geometry is to general relativity as what is to string theory. We don't know whatever that mathematical principle is. We do understand aspects of string theory, special cases. So it's not that we don't understand anything, but we don't know how to really write down the full general theory in its most sort of powerful form. And of course, physicists would like to, we're interested in doing that. And so perhaps by studying some of these mathematical relations, we might be able to shed some light on whatever the mathematics we need is. So, of course, the question is, what is string theory and what's the math behind string theory? And that's a really, really hard and big question. So, as usual in research, instead, let's ask some simpler questions that we might be able to make more progress on. So, one more tractable, but actually still extremely hard question is the following. So, string theory doesn't have any parameters that you can tune. But if you solve its dynamical equations, there are nonetheless many, many, many solutions. There are many estimates of how many there are, but suffice to say it's a huge, huge number of possible solutions to the equation. And so one question you might ask or hope for optimistically is, well, can we at least characterize or organize some of this broad, it's called the landscape of solutions in string theory in some way? Like, it would be really great, although it's not obvious, if there's perhaps a hidden mathematical structure that might help us organize at least some of these solutions and put some order on all of this, chaos that we seem to find. Moonshine observations in string theory point to the existence of very large discrete symmetry groups, and the role in the theory is still being understood. There's a lot of mystery out there, but that was one of the main interests, at least for me, in trying to study these moonshine phenomena. It's about large symmetry groups that maybe can help us organize or tell something about string theory. And something else that's a nice benefit for these investigations is that we learn a lot about special classes of states in string theory that are called BPS states. And I'll explain what those are later in the talk. But basically, anytime there's a nice connection, or at least the vast majority of the time, there's a nice connection between, string theory and quantum field theory, and mathematics, it's usually about these special states called BPS states. They are things that you have when you have what's called a supersymmetric theory. I'll also explain what that is later in the talk. But basically, BPS states are the part of a physical theory that you can formulate mathematically precisely. And so you can make interesting conjectures and even possibly prove conjectures about these BPS states. So much of the connections between modern physics and modern mathematics really uses these special states. And it turns out that they play a role in this story too. Okay. So now let me actually start to explain what moonshine is. So as I mentioned, moonshine is a strange and surprising correspondence between certain objects in group theory and certain objects from analytic number theory. And so what I'm going to do is start by explaining the group theory objects that we need, and then I'll explain the number theory objects that we need and how they relate to each other. And along the way, I'll also tell you a little bit about string theory, just what you need to know to understand this story, so that I can put the pieces together and explain how physics sort of helps unify and explain these moonshine phenomena. Okay. So the first actor in our play, in our story, is group theory. And I know this is more of a mathematical audience, so you probably have seen group theory before in your classes or have heard of it in various contexts. And, to a physicist, of course, group theory is all about the study of symmetries. Physicists are very interested in all kinds of symmetries, which can be codified by group theory. So symmetries are very powerful organizational principles for physicists, always. If a system has some symmetry, it allows us to constrain the physical observables. Things have to respect the symmetry and be invariant under the symmetry transformations. And there are many, many different kinds of symmetry in physics. So just to give a flavor, you can have a space-time background, Euclidean space, Lorentzian space-time, some curved manifolds. That background on which you do physics can have some symmetries associated to it potentially. Or there can be symmetries that act on what are called internal degrees of freedom. Maybe you have some particles that can have a symmetry that permutes them amongst each other or something like that. There are things called global and gauge symmetries, which I won't go into, although I'll talk about gauge symmetries a little bit later. Symmetries in physics can also be approximate, or they can be exact. And all of these things are useful for us. So in particular, let me just contrast two different types. We can have microscopic symmetries. So here I'm just picturing a crystal lattice of some material. So there's a symmetry by translations along this hexagonal lattice. But you can also even have hexagonal lattice symmetries emerging as solutions to equations. So things that are not baked into the equations of the theory, but that are sort of accidental or emergent symmetries of the solutions. So here's another hexagonal lattice that appears as vortices in a superconductor. So even the same kinds of symmetries can have very different origins in physics. And the kinds that I'm going to talk about today are what are called microscopic symmetries, meaning all of the symmetries I'm going to talk about are really symmetries of the formulation of the theory, not any special property of its solutions. So these symmetries are sort of baked in from the beginning. So symmetries of physical systems are those that leave the system invariant, or they're endomorphisms of the system. So in physics and in math as well, of course, the way I would say it is we organize excitations of some system based on how they transform under that symmetry. Or in other words, we just want to study the representation of that associated symmetry group or algebra. A famous symmetry is the symmetry of spatial rotations. So I can rotate my space, and particles in the universe they have to transform nicely under that rotation symmetry. And the label that we physicists put on the representation, we call the quantum number, or for example, spin J for this particular symmetry, which means that those particles have to transform in a 2J plus 1 dimensional representation of the rotation group. So for an example, an electron is spin a half, so it transforms in a 2-dimensional representation of the rotation group. And in physics, those are what we say are spin up and spin down, the two configurations of the electron under the symmetry. And probably the way that you all have learned about these symmetries is that they are codified in group theory. So we have a group, meaning we have some set of elements. I'll focus on finite groups, so there's a finite set of elements in a given group. And they satisfy a multiplication law that's associative. So if I have 3 elements, I can move parentheses around and get the same answer. There's an identity element, and each element has an inverse. So an element G multiplied by its inverse gives back the identity element. So groups are very nice, and they have a simple definition, and they are the way we can mathematically describe symmetries of physical systems. And a natural mathematical question is, what kind of groups can we actually classify? Of course, there's a huge variety, in fact, an infinite variety of kinds of groups. But if we put enough restrictions on the particular type of group we want to classify, there are actually ways to make progress. In particular, the subset of groups that admit a nice classification are called the finite simple groups. So finite meaning that, again, they have a finite number of elements. They're not infinite dimensional groups. But they have, in particular, no non-trivial normal subgroups. That's what it means to be simple. And if you haven't seen the definition before, don't worry about it. You can heuristically think of these as like the prime numbers of group theory. They don't further decompose into simpler subblocks. They're like the atoms of group theory. And you can actually classify finite simple groups. And the classification results were completed in 2004, but it took many decades of effort and huge, the proof is many, many hundreds of pages long by many, many contributors. It's one of, I think, the heroic results of mathematics that this classification of finite simple groups was actually achieved and completed. So it was very hard work, and the results of this classification were the following. There are 18 infinite families. These are sort of the nice, regular, very common groups that you see all the time. For example, the cyclic group of order P for primes P, or the alternating group on more than 5 elements, which are the groups of even permutations of those elements, and others. And again, those are kind of the boring groups that you see all the time, like clock arithmetic and so on. But then there are the oddballs, or the leftovers in these classifications. So there are 26 exceptional cases that also arise in this classification. They don't fit into a nice family. They just are what they are. And they're called the sporadic groups. And Moonshine is about some of these strange sporadic groups that appeared as the leftovers of this classification problem. So it doesn't seem like they should really fit in anywhere, but it turns out that they will. So here are the 26 finite simple groups that don't come in nice infinite families. And the one that I'll talk about the most today is the blue circled one called the monster group. And again, these are finite groups, so they only have a finite number of elements. But the monster group is extremely large. It has about 10 to the 54 elements. So it's not a group that you want to work with in great detail. It has too many elements to really get a nice handle on by just studying all the relations. So as I said, these groups are seemingly in a class by themselves, but they're going to be very connected to a number of subjects in mathematical physics. And what we'll see down the line is that, in fact, the monster group will be a basic symmetry, what I called a microscopic symmetry, of some interesting string backgrounds. Okay. So let me now tell you a little bit about what you'll need to know about string theory for this talk, and then I'll explain the modular form side of Moonshine, and then we'll put it all together. Are there any questions at this point or anything people would like to ask? Okay.
I think no.
No questions? Okay. Then I'll move on, but again, if anything is confusing, feel free to just interrupt and ask a question. Okay, so next let's do a little bit of string theory. So you won't need to know that much for this talk, of course, and I won't assume too much physics. I'll try to explain all the terms that I use. But essentially, in the parts of string theory that we know how to describe and calculate things in, the basic constituents of string theory are, as the name suggests, either closed loops or open threads of string. So it's a quantum mechanical theory, so it's a quantum system of strings rather than a quantum system of particles, which might be more expected or more familiar. You probably have heard that we talk about the electron and, and the photon and things like that. Strings, again, a quantum theory, but the objects are now just one spatial dimensional instead of zero spatial dimensional, like a point particle. And as part of this theory, the strings can interact with one another, just like particles can interact. Open threads can join up, and open threads can also close and form closed loops of string. And closed loops of string can also split and join with each other. And it turns out that open strings can always join into closed strings, like in the middle part of this diagram. But closed strings can't by themselves break up into open strings. So every time you have open strings, you always have closed strings, but you can also have closed strings on their own. And when I talk about particular string theories today, I'll be talking about some of the examples that just have closed strings on their own. Okay, so typically in physics, what we do is we compute probabilities in quantum mechanics. What's the probability that, say, two particles come in? Time is like the vertical axis in this picture. They come in, something happens, and then say two particles go out. And we want to compute the probability. And in quantum mechanics, we sum over all possibilities. So all sorts of things can happen where the particles are interacting with each other. And we draw Feynman diagrams like this to represent contributions to that probability computation. And it turns out that if you add graphs like this with more and more loops, if you make the topology more and more intricate, you're getting a better approximation to the correct answer. So Feynman diagrams are basically organizing essentially a Taylor series. More loops means you're going to higher order in the expansion. And in strings, we do something very similar. We follow the rules of quantum mechanics that we know in physics. So we have two closed loops of string. They can come in and interact and say, for example, two strings go out. But because strings now have one spatial dimension, the corresponding Feynman type diagrams that we draw are actually nice Riemann surfaces. And a great deal is known about two-dimensional surfaces, Riemann surfaces in particular, they turn out to be. And that's a very useful tool to compute a lot of things. So instead of drawing these lines that denote a particle's trajectory in time, which are called world lines, we have world sheets for a string. And you might have heard that there are kind of a few string theories, a few different flavors of string theory. The first one that you see in a textbook is called the bosonic string. It's a good string theory to learn some basics about string theory, but it's unstable. It has what's called a tachyon, so it might not exist at all, or if it does exist, we don't know where the tachyon takes it to, where the end point of the dynamics is. So it's a good toy model, it's a good test case, but it's not very physically interesting. And it lives in 26 space-time dimensions, which is an awful lot, certainly very far from 4 space-time dimensions, 3 space and 1 time, which is what we see in our universe. A bit of a nicer set of examples, where we can also compute a lot of things, are the so-called superstrings. They have an extra symmetry called supersymmetry, which I'll tell you about later. They are stable. They don't have a tachyon, so we don't have to worry about whether or not they even are well-defined mathematical objects. They exist. And they live in 10 space-time dimensions. Still very far from 4, but that's just required by the consistency of the theory, with some caveats, but I won't go into it because that's a whole different discussion. For today, I'm going to use this as not a good model of the universe, but as a way to understand aspects of mathematics. So that's the point of view that I often take when I study this theory. So you might have seen this kind of diagram. It's kind of the most popular diagram whenever people talk about the superstring theories in 10 dimensions. We see these different kinds at the different corners. They're called type 1, type 2a, type 2b, things called heterotic string theories, which are very interesting. When I talk about the string theory models that I made later in the talk, there'll be heterotic string theories in particular. But they're all, even though they end up looking very different, they're all, in fact, known to be related to one another. They're all parts of some mysterious underlying theory called M theory. And as I mentioned at the beginning of the talk, this is the theory that we don't know the full mathematical structure of. We want to find, the analog of the Riemannian geometry or whatever mathematics is supposed to describe this thing. So we don't understand it in full detail, but we understand these little corners. And we also understand, in many cases, how the corners relate to one another. In fact, there's something very important that appears in ordinary quantum systems as well as string theory. It's kind of throughout physics, called string dualities. String dualities are just different descriptions of equivalent physics. They're basically isomorphisms, but they're very, very rich and surprising isomorphisms, and that's why they're so useful in physics. Sometimes they can take one of these string theories to another one of these string theories. And sometimes they even change the background geometry. For example, a string theory on a particular geometric background, some 10-dimensional background, might secretly be equivalent to a different string theory on a totally different geometrical background. So these dualities also tell us a lot about geometry because the strings probe the geometry in interesting ways, and duality gives us many different descriptions of the same thing, some of which we can compute things in more easily than others. So duality is this very, very powerful thing in physics, and it also leads to very precise mathematical statements if you talk about BPS states in particular, which we'll get to. And those can be, again, mathematically formulated. So if you have two different dualities, two different descriptions, you can make, conjectures that they might be equal to one another. So physically, that's where a lot of interesting mathematics comes from. Now, as I said, the superstrings have 10 spacetime dimensions, quite a lot. And people are often interested in trying to figure out, well, what happens if we don't consider 10-dimensional flat Lorentzian spacetime or Euclidean spacetime, Minkowski space, or even R10? What if instead we consider the string theory on a product manifold? Physically, that involves making some of the, we'd like one of the products to be a compact manifold and further to have a very, very small volume, particularly relative to physical length scales of interest. And there's a nice physical procedure to do this. It actually goes back to physicists Kaluza and Klein, and they weren't talking about string theory at all. They were just studying this idea in sort of ordinary quantum systems. They said, what if I started in a 5-dimensional space-time, but then made one of the dimensions a circle, a periodic direction, and made it very, very small? What theory do I get in the sort of large remaining 4 dimensions? And there's a procedure to do this. It's called in physics an effective theory on M. And we also often call it compactification because, we started with a 5-dimensional thing and we shrunk one of the dimensions and made it really small and then went down to a 4-dimensional thing. So you can do this without string theory, but in string theory, it's particularly interesting. And often people like to go from 10 dimensions down to 4 dimensions on a special kind of manifold, which is 6 real dimensions. It's actually complex class of manifolds, so 3 complex dimensions. And they're called Calabi-Yau manifolds, which you might have heard. They have many very nice properties. Mathematically, they're Ricci flat. But physically, the reason this is a nice condition to have is because it turns out that Ricci flatness implies that you can obtain a static, a time-independent solution to the vacuum Einstein equations in 4 dimensions. And since string theory includes not only quantum mechanics, but also gravity, general relativity, we have to be consistent with Einstein's equations. And Calabi-Yau manifolds give us a nice solution that solve Einstein's vacuum equations. And in fact, they also preserve some of the supersymmetry of the original 10-dimensional theory, which was supersymmetric on 10D flat spacetime. And again, supersymmetry for me, I'm not thinking about it as something that might describe the universe, but it's going to be a very convenient tool to connect to mathematics. So what kind of interesting features might we get if we put a string on a compact geometry? So let's just think of the simplest example where I have one periodic dimension here and then some large dimension specifying the length of the cylinder. Well, so here are my closed loops of string, and they have momentum like any other physical object would. So they're traversing the cylinder and they're moving around. And they can also oscillate. So here I tried to draw some, oscillations or excited states of this string. But because strings, unlike particles, have one spatial dimension, we can also have non-trivial topological sectors. In other words, the string can wind around this compact direction once we have it. So this has winding, what we call a winding quantum number of 2, because it winds around twice. So strings carry momentum and winding when we have a compact geometry, as well as oscillator modes. And one of the things about string theory is that different oscillation modes of the string actually describe the mass of particles that you can observe in the large space-time dimensions. So the more the string is excited, the more massive a particle you'll find. So here is a simple formula relating the mass squared of particles in space-time to these properties of the string on my compact direction, my circle that I just mentioned. So r is the radius of my circle. L sub s is the length of the string. And here you see the momentum and the winding numbers and the oscillator numbers. This formula is in particular just the formula for the bosonic string compactified on a circle, because it's the simplest one I can write down. But there are generalizations for the superstring and for the more interesting compactifications on Calabi-Yau manifolds, etc. So just imagine that there are analogs. But let me just show you the simplest equation. And I want to emphasize, I wrote this equation down because I want to emphasize something. So notice that this equation is symmetric. In other words, I'll get the same mass squared if I exchange the momentum and winding numbers, but also take r to the string length squared over r. In other words, compared to the length of the string, I'm basically inverting the radius of the circle. That doesn't change any of the physical particle masses from that equation. And it turns out that that relationship, it's not just a special property of this particular equation, it's actually a duality or a deeper symmetry of the theory on the compact geometry itself. And it's our simplest example of a duality that relates strings on one spacetime to strings on a different spacetime. In particular, in one frame, I have some momentum and winding states, and if I say I have a small radius r. But this tells us that that's equivalent to string theory with the momentum and winding numbers swapped, but now on a very, very large radius circle r. If r is small on one side, the string length squared over r is going to be large, and vice versa. So again, string dualities relate string theory often on very different background geometries. So they relate different geometric properties to each other. And if you try in string theory, well, what if I just wanted to try and shrink all of my compact directions down? What if I really wanted to go from 10 dimensions to 4 dimensions, and I don't want any of this extra 6-dimensional stuff? Can I just make the compact manifold really, really small so it's basically not there at all? And the answer is no. String theory says you cannot do that because it in fact is equivalent to a geometry where the compact manifold is very, very big. Essentially, there's a minimum length that you can see. Things can be as small as the string length, but not any smaller. You won't be able to shrink the dimensions away or get rid of them. And this duality in string theory is called T-duality. So I just want you to remember the name for later in the talk. And as I said, this was just the simplest example, but there are generalizations of this idea. Okay, last little bit of string theory because it will actually connect to modular forms pretty soon. So that's why I'm showing you a few more formulas. Let's say we just want to count how many states our string theory on a particular background has. That's kind of one of the simplest physical observables you can ask about. Just how many states do we have? And we like to organize these by, say, the mass or energy of the corresponding state. So how many states at a given energy or a given mass? We call this the partition function, so we denote it by Z. Physical states live in a Hilbert space, which is a complex vector space with a Hermitian inner product. And so to compute the partition function, we take a trace in this Hilbert space, so physical states are actually rays in this Hilbert space, we take the trace and we weight it by e to the minus beta h. H is what's called the Hamiltonian, and beta is related to the temperature of the system. And don't worry about it if you don't know what these things are or haven't encountered them. It's just the thing that measures the energy for us so we can keep track of it. So we'll have some sum where C of n are the number of states at the given energy level n, and Q to the n is just a formal parameter that's keeping track of the energy for me. So that's the definition, but how do I compute this? There's a trick to do so. This slide is more if you have some familiarity with physics. If you don't worry about it. But there's actually a nice correspondence that tells you that the partition function of a quantum object can be computed using what's called a Feynman path integral for that object if you take your time direction, make it Euclidean, which involves multiplying by a factor of the imaginary unit. So you treat it now just as another spatial dimension. There's a trick to do so. And further, make that now spatial time direction periodic. So you make it a circle of some radius. And there's a formal argument that shows it. I won't tell you the details. But if you do this, if you have a string, that tells us that the partition function is defined on a two-dimensional torus, because you have one circle being the closed loop of string. And if I make time a Euclidean direction and also periodic, then the string will kind of move around and come back to itself. So it'll have the topology of a two-dimensional torus. So the important point of this slide is just that string theory partition functions are defined on a torus. That's the main point to keep in mind. Okay, so with that, let me introduce the final mathematical ingredient before I can put all the pieces together. And these are modular forms. I'll suppress some important technical conditions in this talk, but there's a really nice textbook by Don Zagier, for example, that gives you all the precise mathematical definitions. So here, what's the basic definition for the purposes of this colloquium? So let's say we have a group of 2x2 matrices with integer entries and determinant 1. That's called the special linear group, SL2Z. And let me also define a complex variable tau. Actually, tau doesn't need to be defined on the whole complex plane. I just need it defined on the upper half of the complex plane, so positive imaginary part. That's not too important to understand for today, but just turns out to be true. A modular function is simply a function that's invariant under the natural action of tau by the group SL2Z. So tau goes to a tau plus d, excuse me, that's a typo, a tau plus b over c tau plus d. And a function is a modular function if it's invariant under that transformation, under that particular group. There's also some important analyticity conditions, but I won't go into that today. So SL2Z as a group is actually only generated by two generators called S and T. So they're matrices that look like this. So if you plug in S, that takes tau to minus 1 over tau. It's like an inversion. And T, if you plug in the transformation, takes tau to tau plus 1. It's a translation in T. And any other element in SL2Z can be written as a linear combination of these basic generators with integer coefficients. Okay. So modular functions are a very nice class of functions that are very symmetric under this particular group, this group of 2x2 matrices. Actually, there's a geometric interpretation of the group SL2Z. It's what's called the group of large diffeomorphisms, or the mapping class group of the torus. Let me unpack that a little bit if you haven't seen it before. So here's my complex plane, and here's the upper half of the complex plane, and I'm drawing a two-dimensional lattice. So I can normalize this vector to just be length 1, and then this other complex vector I can parameterize by tau, telling me where that's pointing. And it's a lattice, so I want to imagine that these two vertical lines are identified with each other, and these two horizontal lines are also identified with each other. And if you identify those two edges of the lattice, you'll get a torus topology. You can see that by just rolling up some paper. So what these groups of symmetries are, these mapping class groups, are essentially change of bases of this underlying lattice that give geometrically equivalent tori, roughly speaking. So to a physicist, it's just like a change of coordinate system or a change of basis that shouldn't affect a physical observable. So it's kind of natural to imagine that you want to only consider tori up to the action of SL2Z, where if you have two tori whose parameters or whose lattice parameter tau is related by SL2Z, then we treat them as the same torus. And here, in fact, is the upper half plane of the complex plane. And the shaded region is actually the set of values of tau, such that you can get to any other point in the complex plane by SL2Z transformations. So this is called the fundamental domain. It kind of encodes all of the non-trivial tori that are not equivalent to one another. And you can get to any other point just by acting with SL2Z, and you'll get equivalent tori. So here I can act by T and move over here, and I can act by T again and move over here, and so on. Okay, so this SL2Z has a geometric interpretation. It essentially is about some sort of symmetry of a torus. Modular forms are very prominent in number theory, since often you can write them as an expansion, and coefficients of that expansion tend to be very interesting expressions involving various integers. And since the functions themselves are highly constrained by modularity, you can often get very interesting relations among these integer coefficients, so you can prove number-theoretic statements using properties of these functions. And they're central ingredients in some very deep proofs, such as Fermat's last theorem and optimal sphere packing, for which Marina Vyazovska became the second woman to win a Fields Medal. I don't have time, of course, to explain how and why they appear, but just to give you the sense that these are important objects in a particular part of mathematics. Okay, one last piece of terminology, and then I'm going to start tying everything together for you. So you might have heard that in topology, the number of holes an object has, it's called its genus. So a sphere is genus 0, a torus is genus 1, and so forth. And some modular functions have a very important property called the genus 0 property, which is central in the statement of the Moonshine conjectures. Formally, the statement says, if you have not just SL2Z, but some subgroups of SL2R, and you consider their fundamental domain, the analog of the shaded region I drew on the previous page. In other words, it's the quotient of the upper half plane by that group. I can ask what modular forms or what corresponding modular functions are there that are modular with respect to whatever that subgroup is, similar to the SL2Z example I showed you. It turns out that if this fundamental domain has the topology of a Riemann sphere, so here's the fundamental domain for SL2Z. I've identified important sides and drawn out infinity and so on, and it's this like very pointy sphere. Then all modular functions that are invariant with respect to that group gamma can be written in terms of one single special generator f of tau. So there's one modular function for that group, and every other modular function that's modular under that group can be written as a rational combination of that f of tau. And modular functions only have that one special generator if the fundamental domain is called genus 0. So that's a very special, very rare property of some types of modular functions. It's often called the Haupt module or principal modulus, just a name. So SL2Z, as I said, is genus 0. The fundamental domain has the spherical topology, and its generator is called the J function. So here is a function, I've written it as a function of tau. It's modular, so it's invariant under tau goes to tau plus 1 and minus 1 over tau, the T and S transformations. And it's often convenient to write Q as e to the 2 pi I tau. And if I do so, it has an expansion in Q, and the first few terms look like this, where I'm expanding around tau goes to I infinity. Okay. And now all of those ingredients can finally come together. So I told you that string theory partition functions live on a torus, and we have a torus here in the modular world. This mapping class group, or large diffeomorphisms, these SL2Z transformations, for example, are nothing but symmetries in a string theory, such that all physical observables have to be invariant under that symmetry. In other words, this is like a change of basis of the lattice, and the physics doesn't care which basis you choose if it leads to equivalent tori. Physics can't tell the difference, which means that a partition function, which is a physical observable, has to be invariant under change of bases, which means the string partition function, which lives on the torus, has to be invariant under SL2Z. In other words, string theory is very, very good at producing modular functions. It's extremely good at that. All of the partition functions are these nice modular objects for various groups gamma. The groups don't have to be genus 0 necessarily, but it's natural from a physical point of view. So Moonshine goes as follows. Let's look at the J function, which is the special generator for SL2Z in particular. That's our favorite example. So we have a Q expansion like this, and the mathematician John Mackay, who is a group theorist, in 79, he wanted to take a break from group theory, and he was reading a number theory textbook. And he happened across the J function, since it's such a central object in number theory, and he was looking at its expansion coefficients in Q. And being a very powerful mathematician, he noticed that 196,884 is 1 plus 196,883. A very powerful mathematician can see that that's a true equation. And there are similar decompositions to the other coefficients. But okay, why on earth would one want to write those integers in that way? Well, what he noticed was that all of the coefficients of the J function could be written as sums of dimensions of irreducible representations of the monster group, the largest sporadic simple group, that strange group from group theory that seemed like it had no place and wasn't involved anywhere for any reason. Any representation of a group can be written as a sum of irreducible representations. So that's telling us that the J function is somehow, it knows about some representation of this monster group. And Moonshine was born from that observation. Why should that be true? Why should these things have any relation to each other whatsoever? It's very strange. Now, what a physicist might say, and in fact, even a mathematician, they thought of this before physicists did, although it turns out to be very natural from a physical point of view as well. They said, well, okay, let's suppose that there is some infinite dimensional vector space that is a representation of the monster group. And it can be graded somehow by integers from n equals -1 to infinity, so that each level n has a finite dimensional representation, and we sum them all up in a direct sum to produce an infinite representation. And we call that representation, for historical reasons, V natural. Say that representation exists, and suppose that J of tau should be interpreted as a function that's just keeping track of the dimensions of that vector space at each level n. So then the dimensions of that vector space at each level n would be the coefficients of the expansion of the J function. And another way to write that in group theory is the character of the identity element of that representation. That's equivalent to the dimension. So physically, you might say, well, I just want a physical system whose Hilbert space has a monster group symmetry that commutes with the Hamiltonian. If it commutes with the Hamiltonian, then at every energy level or mass level n, the coefficients should decompose as a representation of that symmetry. That's just basic physical principle. But the question is there a nice physical system that has that symmetry and whose partition function is the J function? Such a theory was not known or constructed at that time. We didn't know what V natural was. What Mackay and Thompson did was they tried to make some progress by just generalizing the J function and looking at other modular functions. They said they were formally able to compute functions called T sub G, which instead of looking at the characters of the identity element, they looked at characters of other group elements of the monster, and they looked at what kind of functions they got there. Now, remember, the monster group has 10 to the 54 elements, so you don't want to deal with 10 to the 54 functions. You can't. But in the trace is cyclic, so actually these functions only depend on the conjugacy classes of the group, not the elements. And it turns out there's only 194 conjugacy classes of the monster, which is still a lot, but it's a lot better. And so the monstrous Moonshine conjectures were then made by the mathematicians John Conway and Simon Norton. They conjectured that the Mackay-Thompson series, all of these Tg of tau, including the J function, which is like T1 of tau, are actually the generators of genus 0 subgroups of SL2R. Again, rare, special modular functions. Not many symmetry groups have privileged generators like this. The genus 0 condition is very rare in modularity. And Borchards was able to prove this in 92, and he was awarded the Fields Medal for proving this conjecture in 1998. And there's a physics explanation for it. So let me start by telling you the basics, and then I'll tell you what I contributed to it later. So as you might expect, because I have a torus and I need a modular partition function, I'm considering string theory. And there's a particular background on which you can put string theory such that the theory has monster group symmetry and whose partition function is the torus. That at least tells us part of something about the monstrous moonshine conjectures, although it doesn't tell us about genus zero. The special background uses another exceptional mathematical object called the Leech lattice, which is one of the 24 even self-dual lattices in definite signature in 24 dimensions. So another special object from lattice theory shows up. Actually, you have to do something special to this background, which I can't quite tell you about. It involves words called orbifolds conformal field theory, or if you've heard of vertex operator algebras, that's sort of the mathematical name for it. And such a mathematical object was constructed by Frankel and Lepowsky and Merman precisely to describe V natural, and later people were able to understand it from a string theory point of view. So that kind of gives us some of the physics. There is a physical system that has the symmetry and a modular partition function, but it doesn't tell us why all of these Mackay-Thompson series are the special and rare functions of the monstrous moonshine conjectures. Why are they all genus zero? That doesn't make any sense. And it's not obvious that physics should have anything to say about it, because it's not a very natural thing for a physicist to think about. So in the last 10 minutes, let me tell you a little bit about my work, which I think closes that loop and puts all the pieces together. So the story that I just told you about, this string on the Leech lattice background, that involved the bosonic string, which again is unstable and not desirable. And I want to use a superstring instead to build a new model. And superstrings have an extra symmetry, which relates what are called bosonic and fermionic particles to each other. This symmetry is called supersymmetry. And as I said, the important thing about a supersymmetric theory is that it has special objects called BPS states. BPS states in a theory can also be counted separately from any of the other states. So rather than compute a partition function, you can compute something simpler, which we call an index. And indices often have very precise mathematical definitions as well, in many supersymmetric examples, which I won't go into, but it also underlies many other nice connections to mathematics and physics, including many works by Witten and others. These indices are actually really computable. They're much simpler to compute than the partition function of a general theory. So if you can't compute a partition function, but you have supersymmetry, you can still compute an index. And so if you compute it, say, when the strings interact very weakly and perturbate, and you can do your Taylor expansion and just compute everything very easily, it turns out that that's also true when the strings are very strongly interacting and things become harder to compute. So you can learn a lot about dualities, in particular, by studying BPS states, because dualities often take weak to strong coupling as well, just like they took small radius to large radius. They change parameters. Okay, so what's a BPS state? So a supersymmetric system has this extra symmetry called supersymmetry. Infinitesimally, we can write it as a Lie algebra, which is what's called a fermionic or super extension of the Poincare algebra. Poincare algebra is the symmetries in Minkowski space, for example. So normally with a Lie algebra, we define the commutator, the elements AB minus BA. But in a superalgebra, we also have additional generators, which I call QA and QB, which anti-commute, meaning we look at QA, QB plus QB, QA. And a lot of nice physics follows from this just change. In particular, the anti-commutator of these quote-unquote supercharges, these new generators, is related to the energy and momentum operator of a theory, or the Hamiltonian, which I've talked about before. And so BPS states are simply the states that saturate a lower bound on this particular commutation relation. In other words, they're killed by some of the supercharges. Physically, they're the lightest states of a given charge, meaning they can't decay, which is why they're so stable and we can study them in all kinds of different regimes. So in particular, the simplest supersymmetric algebra has one supercharge Q, Hermitian conjugate Q dagger, and they anti-commute to the Hamiltonian. Which means if I want to study a physical observable, like an expectation value, Well, I get something positive definite and bounded from below at 0. But because of this anti-commutation relation, that tells me the Hamiltonian is bounded from below and the lowest state is at 0 energy. And the BPS states of these systems, which saturate this bound, are nothing but ground states of the Hamiltonian, the 0 energy states, supersymmetric ground states. And they're counted by an index, which is called the Witten index, which is very much like the partition function we met, but there is an extra -1 to the f in there, where f is the fermion number. So it acts with a +1 on bosons and a -1 on fermions. And it turns out that because of supersymmetry relations, if I have a state with non-zero energy, all of the bosons and fermions come in pairs. So in the index, they all cancel out. Bosons minus fermions, equal numbers of them, they all cancel. The only time where you don't have this strict relation is for the 0 energy states, precisely the ground states or the BPS states. And there the Witten index just computes the number of bosonic ground states minus the number of fermionic ground states. And of course, it's just a number, it's just an integer. It's not a complicated function like the partition function. It's the simplest example of a supersymmetric index. So finally, let me sketch how all of this helps with monstrous moonshine. In grad school with my collaborators Person and Volpato, we built a superstring compactification, and we used this special V-natural as part of the ingredients. But instead of computing a partition function of this theory, we computed a BPS index. And it turns out in the particular model we were studying, the BPS index gives this famous identity for the J function. It's a number-theoretic identity by Coloquio, Norton, and Zagier, and it tells us that if you subtract two J functions with two different variables, it satisfies a very beautiful infinite product identity, where these exponents are given by coefficients of the J function. This identity was also used by Borchardt to brute force compute the monstrous moonshine conjectures. He used formulas like these to show that the functions had to be genus 0, but Borchardt's proof didn't actually explain why they were genus 0. There are similar identities for all of the TG, by the way. But in string theory, things make a lot more sense. These formulas are actually related to a new hidden symmetry that organizes the BPS states in these models. They're called generalized Kac-Moody algebras, so another beautiful object. And generalized Kac-Moody algebras were actually originally defined by Borchardt and used in his proof, but in our superstring models, they have a physical interpretation. And most importantly, I think we were able to show that all of these genus 0 groups of monstrous moonshine naturally arise as T-duality groups in our string theory model. So I told you about T-duality earlier, and for the particular model that we're studying, there are groups of interesting T-duality transformations, and they're actually exactly the groups of monstrous moonshine, and they're genus 0. So in the superstring model, we were able to understand things physically a lot better, even the genus 0 property. And so we were able to fully recover the monstrous moonshine conjectures from a physics point of view. And I think it was really nice that string theory was able to tell us this, even though it wasn't at all obvious that physics would necessarily know about this formal aspect of modular functions. I'm going to wrap up shortly, so let me just tell you that there's other examples of this sort of thing for other sporadic groups, and I studied them along similar lines with collaborators. So my perspective as a physicist is that supersymmetric string vacua can have really interesting duality groups. And in particular, if you compactify to very few large space-time dimensions, like the example I showed you for string theory, I told you it was compactified on a 24-dimensional torus based on the Leech lattice. Remember, all tori are based on lattices, and the Leech torus is a 24-dimensional torus. So if you take a superstring, if you take the bosonic string and compactify it down on 24 dimensions, you only have 2 dimensions left over. The superstring models that I constructed are also very similar. They live in very low dimensions. But sort of the more you compactify string theory down, the more interesting the duality groups become. Sometimes, as I told you in this talk, they accommodate exotic discrete groups like the monster. And so I think it might be one interesting suggestion is perhaps one can organize simple string theory solutions by taking a theory, compactifying it on very low dimensions, getting a really big duality group there, and then maybe trying to slowly take decompactification limits and see how that big symmetry group might break or change, and if that can help us organize some of the structure of these solutions. Finally, a connection to math that is very well established by now and very interesting is that BPS quantities in string theory always have to be in duality invariant. That's why our JT minus JU identity was invariant under SL2Z in particular. Similarly, for the TG, they're invariant under the gamma G groups. And even in much more complicated and other compactifications, a BPS index always has to be invariant under the duality group because it's a symmetry. And that means they're always what number theorists call automorphic forms. So there's a very rich, very beautiful generalization of the modular form story to things called automorphic forms for other kinds of groups, and it leads to a lot of beautiful number theory connections in string theory. And that's been studied by many people. So I hope one can understand all instances of moonshine physically, but I think that that's a nice story. So I'm out of time, so let me just conclude and say that moonshine is a rich story that connects a lot of areas of math and mathematical physics, especially modular forms and finite group theory. And it turns out that you can explain a lot of these phenomena in string theory, and that tells us a lot about physics as well. So that's it, and thanks for your attention.
Thank you, Natalie. And this interesting talk. Well, we to move for the question. If anyone have a question, please. Well, I think no have a question.
Okay.
Thank you, Natalie. Thank you very much.
Yeah, thank you. Hope you guys enjoyed it.
Well, it was a great